Have you ever wondered how mathematical analyses go beyond just solving equations? What if I told you that mathematics is not just about numbers, it is about deciphering the very fabric of the universe? What about understanding the probability of your favorite sports team winning the championship? From the mind-melding realms of calculus to the logical intricacies of discrete mathematics and the mesmerizing patterns of fractal geometry, the world of mathematical analyses is vast and ever evolving. In this video, I will be guiding you on this mathematical journey, breaking down the concepts and answering those burning questions which you might have. So whether you're a student looking to ace in math class or just someone who have always been curious about the magic behind the numbers, get ready to embark on a journey of discovery and exploration. My name is Shaunak and you're watching this video on my channel where we are discovering, understanding and finding the deep significance of different mathematical analyses. Well, before I go ahead and start this video, I would like to express my thanks to one of my subscribers. This video would not have been possible without you. Yes, I am talking of this person, Shashank Shahi, who have put up a request few days back talking that what is the difference between analysis, mathematical analysis, etc. Thank you for your videos. God bless you. So a big note of thanks to Shashank Shahi. Shashank, thank you very much for this wonderful suggestion because it's a new learning for all of us and I think I can make up to your expectation and to the expectation of all the subscribers across the globe. So thank you very much, Shashank, once more a big note of thanks. And now we would start with what are the objective, why I'm making this video right now. So you see, the basic objective of this video is to understand what is analysis. We also need to understand why do we need the analysis. We also need to understand what are the different branches that exist in analysis because we need to understand the basic difference between those analyses. So that is basically the objective of the video and that is what we are trying to make up. We will also look into some of the practical aspects, I mean to say the industrial application, how it benefits mankind, because any scientific or mathematical discovery or endeavor is not fulfilled until it meets up the demand or do some good thing to human being. So first, having laid the objective today, we would first like to understand what actually is analysis and further we go ahead. So as you see here that as we always talk that origin is always from the Greek word which is this, which usually means a losing or releasing something, a dissolving, resolution of a whole into its parts or a breaking up. Now what I am trying to mean is that from this Greek word what we can understand analysis is something which is breaking up, dividing, dissolving and then going into understanding those things. So let me give you a quick literary example which will make things more interesting. If I say he had short black hairs and steady grey eyes and I say that his face was square, his nose is Roman or was Roman, then definitely I can deduce from that that he was a ruggedly handsome fellow. So what do I mean by that is that the first two sentences are actually providing the facts, the black hair's color and the steady grey eyes and the configuration of the nose being a Roman, and from there the third sentence tells that it is basically nothing but an interpretation. So from there we deduce something that it is the process of breaking a complex topic or any substance into similar part so that we can get a better understanding. So analysis is an interpretive process that draws conclusion from basically a set of facts, and it is the scientific process of examining something in order to find out what actually it consists of. So these are basically from the Greek word. We understand it is breaking down, it is dissolving, and it is something from those breaking parts so that we can understand things, examine things more effectively and more scientifically. But the question is that whenever we talk about analysis, the first thing that comes to in our mind is mathematics. Now my question is that is analysis only related to mathematics or something more than that? Let us look into the next part of our video. So the concept it tells of analysis is not only related to mathematics, it can be related to scientific analysis. Obviously, in scientific, chemistry, physics, etc., astrophysics, everywhere we do a lot of scientific analysis. It can be also related to business analysis. The fact is that in business, forecast, cost, pricing, the entire consumer behavior revolves around business analysis. It can be related to computation analysis, as we see data science, deep learning emerging day by day. So analysis is also playing a significant role in computation. Well, financial analysis and business analysis goes hand in hand, but financial analysis is something more into the finance part, where we find out the consumer, cost, product, and a lot of companies, do a lot of financial analysis. They put a lot of budget in order to know so that their product runs well and the sale goes up. We also do a lot of linguistic analysis. This is really something very important, because in language and linguistics we do a lot of analysis in order to know the ethnicity, where from the language came, where from the symbols of Latin, Roman, Greek, Chinese evolved, and what is the basic psychology of that. It's a very interesting subject called linguistic analysis. We do a lot of literary analysis, starting from poems, prose, etc. We do a lot of analysis. We try to find out what the poet says, right from the primary school up to the PhD level. Literary analysis really occupies a huge area. We also do musical analysis, isn't it? Because from the Eastern classical, the ragas, the tals, etc., to going up to Beethoven, Mozart, Haydn, where we do a lot of musical analysis in terms of symphony, etc., musical analysis do play a significant role. We do a lot of psychological analysis in order to understand mental aberrations and thereby help and cure people having psychological problems. Statistical analysis, which is the most prevalent in all the fields of mathematics, helps us to grow, study consumer behavior. And finally, we get into mathematical analysis. So the question is that these are the wide variety of analysis. There is no point to understand that analysis would be only and only related to mathematics. Other than mathematics, the entire world revolves around something with analysis, and we are taking up mathematical analysis because the channel and everything is related to mathematics. Fine, so we can subdivide each of these categories, scientific, business, computation, into certain other divisions, but that is out of the scope of the video. So what we understand is that analysis, most importantly, it has nothing to do with mathematics. Now, we saw that analysis is breaking down a complex entity into individual components. Why? Because by breaking down, we can understand, examine, and do the understanding of the relationships and the characteristics much better. So what is the goal? The goal is basically to gain insights. We need to identify complex patterns, and we need to extract certain meaningful information from the elements being studied. For example, topology, astrophysics, mathematics, business, economy, whatever we saw just now are basically breaking those things into small individual bit size so that we can do something much more significantly. Now there is an anti of analysis which is called synthetic analysis, that is called synthesis, that is combining different elements often derived from the analysis process to create a new integrated whole or solution. So that means it is just the opposite. Analysis is breaking down those concepts, and synthesis is basically combining or adding or integrating those concepts. Why? Because we need to find out a whole solution. In a synthesis, as you see, we take the insights and information obtained from analysis, and then we help up into bringing up a innovative or cohesive design. So here it goes. Analysis is magnifying, breaking up, identifying patterns, and converse is the synthesis, where putting up the pieces back together gives us some meaningful understanding of the whole the whole summation, the holistic understanding of the thing that we are stuck into. The question rises that we talk of analysis in mathematics, but is mathematics, or does mathematics have something to do with synthesis? So yes, is there something which is called a mathematical synthesis? Well, really, you can see that certain algebraic expressions, I've just given certain very fictitious numbers. So these algebraic expressions can be, synthesized together, maybe to understand a difficult, complex algebraic expressions. So aren't we doing a mathematical synthesis over here, where we are adding adding up certain individual components, complex components, which we obtain from mathematical analysis and making a synthesis. Also, so you might synthesize various algebraic techniques in order to solve a bigger problem. The same happens with geometry. Maybe we are taking certain complex understanding of geometrical patterns and we get a better understanding of the geometry. So in geometry also you might synthesize different geometric objects to get a holistic understanding to prove a certain theorem, axioms or anything like that. So from here I just wanted to tell you that this part of the video just shows you what is mathematical synthesis, although we talk only of analysis, but yes, synthesis also exists, which is integrating, adding things together in order to get a holistic approach of a complex thing. So here it shows that mathematical synthesis is possible. Now we come to the question that we understood what is analysis. We understood analysis is nothing which is only related to mathematics, and we saw the huge spectrum of analysis around the world. Now we come to the central part, is that if we take mathematical analysis, then what actually is mathematical analysis, coming up into the next part of our video. So you see, mathematical analysis basically focuses on understanding and exploring the properties of functions, sequence and limits. It is something like, for example, when you zoom in or out, how do you zoom in and you find fine graining details, and then you do a mathematical analysis. So if I take this left hand side, say for example of this figure to be calculus, and we do all those things, isn't it? Sequence, limits, derivatives, continuity, integrals, we are doing all those things. We are using these formulas, we are using this system in order to get and do well in calculus. Now the same thing on the right hand side, if I take a mathematical analysis, I am doing the same sequence, same limit, same derivative, same continuity, same integral, but what we are doing is that we are trying to find out a rigorous analysis. We are trying to find out how it happens, where it happens, which components are responsible, and when does it happen. So we will soon understand what do we mean by the term rigorous analysis. This is a qualitative understanding, but we need to quantify that. But before that, I want to make a point that this is actually what is mathematical analysis. All those sequence, all those limits and derivatives, whatever we are doing in the calculus, when we do a mathematical analysis, we do a more rigorous understanding, how, where, which, when, and so on. So you see, these formulae which played a role in calculus, where we plug and play and solve our equations, engineering, practical problems, these are no more formulae, these are no more plug and play, but we are trying to find out how sequence happen, what actually makes limit happens, what is the root cause of the derivatives. So this is actually what is mathematical analysis all about. So we can define mathematical analysis to provide a rigorous foundation for the study of change and approximation. Let us take calculus for the time being. Let us understand real analysis we are taking into calculus, then we will migrate to the other areas. Now when I underline this as a rigorous foundation, I need to define what is a rigorous foundation. Simple, when we are trying to find out the area under the curve, if our method is not rigorous, we may get a wrong answer, obviously. So that is what is called rigorous. But hold on, there is a much better understanding of what is a rigorous mathematical foundation. So first thing is that it has to have a precise definition. That means whatever the term that we are defining, it should remove all the ambiguities and ensure a clear understanding of its meaning. It should also have logical deduction, because it involves axioms, definitions, and what has been previously proven. It should have proofs, and this proofs has to be rigorous. There should be watertight, and there should not be any kind of a way where we can find out any loopholes in the proofs. We also need to have something which is called an axiomatic systems. It is a huge branch of mathematics, but however, axiom serves the basic foundation of rigorous mathematical foundation. And then we come to something which is called consistency and coherency. Without a consistency and coherency, any mathematical foundation will be shaken and the entire pyramid will collapse. So what I think is that this is what do we mean by rigorous mathematical foundation. Definition, logical deduction, proof, axiomatic system, and a very good consistency, coherency should make up the rigorous mathematical foundation. And this mathematical foundation is basically the basically the foundation, the cornerstone of what we call is a mathematical analysis. So here it is, a clear and a summarized explanation. In mathematical analysis, we are doing everything, function, sequence, etc. But how we are doing? We are doing this to find out a more precise definition, more logical deductions, proofs, axiomatization, consistency, clear notation, verification, and peer review. And we should avoid everything, all fallacies. And these things are applicable to physics in different ways. It is applicable to engineering, and it is applicable to economics, and it is also applicable to finance. We have just seen that. So this actually shows what actually is mathematical analysis, the root cause being the foundation of mathematical analysis, being the rigorous mathematical foundation. And what defines the rigorous mathematical foundation? Right hand side on the screen, you can see all those things are more precise and logically deduced without finding any fallacies. Now the question is that what are the different branches of mathematical analysis, and what is the role that it's play? Coming up into the next part of our video. So what are the different branches of mathematical analysis? I will take some basic idea, otherwise it would be too long of a video. So first what we take is calculus, which we already know is a real analysis. So calculus is a part of real analysis concerned with functions and how do they change. And real analysis, I think I don't need to explore or expand too much. It includes topics like limits, continuity, differentiation, and so on. We next come to what is very important and interesting, which is called a functional analysis. It studies spaces of functions, operators, and other things. Concepts like convergence and compactness are dealt with. We will look into that, don't worry. We find something which is called a harmonic analysis, and harmonic analysis actually represents functions of signals, a superposition of basic waves, techniques like Fourier analysis, etc. Don't worry, we are also going to look into that, but something which is related more into signal processing. We also have something which is called a measure theory. Now here this is something real heavy mathematics, where it provides a foundation of the understanding of length, area, volume, and integration in a more general settings. That means the Lebesgue integration and others, these are much more generalized, where even the measurements of concepts of length, etc. are much more generalized. So that is what measure theory does. It is a part of mathematical analysis. We also get something which is called numerical analysis, and is a study of algorithms which I would say solve problems and find out approximations, not an exact understanding. Here it is, non-standard analysis, very important. It is an alternative to calculus and real analysis, and it introduces infinitesimal and infinitely large numbers in a very rigorous method. We also have what is called a stochastic analysis, which deals primarily with the probability and the probability distributions. By this time you already know. And we also do with PDE, that is partial differential equation analysis, which focuses basically on involving multiple variables and multiple partial derivatives, which are also qualitative behavior of PDEs. So this is something we would start with, and we will look into this. This is called non-standard analysis, and apart from that, we also have vector analysis, which deals with, you can say, vector calculus or something like that. We also have scalar analysis, which is a branch of mathematics dealing with scalar values. And we also have tensor analysis, a huge subject. I think I've got good videos on tensor calculus and how vectors and scalars and how tensors also play a vital role in Einstein's general theory of relativity. So among all those mathematical analysis, what we do is that first we start with something which is called a non-standard analysis, and this is the person who is the inventor of non-standard analysis. It is called, his name is Abraham Robinson, a mathematician who is most widely known for development of non-standard analysis, a mathematically rigorous system whereby infinitesimal and infinite numbers were reincorporated into modern mathematics. Nearly half of Robinson's paper, if you read, are applied to mathematics rather than in pure mathematics. So here it is, non-standard analysis is actually a kind of a mathematical framework which provides an alternative approach. Now, I'm not going to go why we are providing an alternative approach, because again it would take a long time to expand on the limitation of Leibniz and Newton's calculus, but actually it is reformulating the calculus using a locally rigorous notion. So what is the key idea? The key idea is this. It is to extend the real number system to include infinitesimal numbers. That means numbers that are smaller than any positive real number but still greater than 0, and infinitely large numbers that are greater than any standard number. So basically the extension intuitively allows the natural treatment of concepts like limits, derivatives and integrals. And this is what we can say about non-standard analysis. It deals with something which are called hyperreal numbers. These are not reals but hyperreal numbers. So it includes standard real numbers as well as infinitesimal and infinitely large numbers. So you see that what we are doing, we are standardizing, we are incorporating everything one. This is a very important principle. It states that if a statement is true for the standard real number, it will also be true for hyperreal numbers. Although remember, non-standard analysis have undergone a lot of criticism. Infinitesimal calculus. Non-standard analysis simplifies the treatment of calculus by allowing infinitesimal quantities. It also uses standard part function which extracts the standard component, and this is SIA or smooth infinitesimal analysis, which is a kind of a variant. It is not a standard, it's a variant of non-standard analysis that actually focuses on smooth functions and smooth infinitesimal quantities. Obviously, if it is calculus, it has to depend or rely upon something which is called a smooth function. Taken together, here is the final thing. Non-standard analysis actually proves many theorems, including the fundamental theorem and the L'Hopital rule. And it has been used to solve problems in other areas of mathematics, although severely criticized. So this is what we call as a non-standard analysis. But when we talk of calculus and extending it to non-standard, what comes into our mind are waves, our frequencies, our signals, and that is what we are covering in harmonic analysis. Now actually the origin starts from Jean-Baptiste Joseph Fourier, a French mathematician who actually pioneered the concept of Fourier transform. So we can say that it is a kind of a branch of mathematics that investigates the connection between function and its representation, obviously in terms of frequency. So it is all about frequency, representation of Fourier transform and periodic functions. So definitely we can represent many physical phenomena, and it's got a lot of usage in sound waves, electric currents, etc. So such motions can be measured at a number of successive values, one after the other, something like this. So waves, frequencies, sound waves, currents, signals, these are actually whatever the branch of mathematics that studies, this is called harmonic analysis. Let us look into what are the aspects important of harmonic analysis. First is obviously by default the Fourier series, which expresses a periodic function as a sum of sines and cosines. Then we found frequency domain analysis, which deals with the transition between the time and the domain. You see everything related to waves and signals, so it is quite evident. It is applications in signal processing like filtering, compression, noise reduction, everything. Spectral analysis, it is used in fields like audio processing, image processing, etc. Quantum mechanics, definitely. I have earlier expressed in a video how Heisenberg's uncertainty principles root cause is basically the Fourier analysis, and obviously musics and acoustics, it helps to explain the timbre and harmonics and do a lot of musical analysis. So you see that musical analysis is again related to harmonic analysis. It also deals with data analysis because a lot of periodic patterns in time and series are related to data. Fluid dynamics, yes, because it is helped by harmonic analysis. Geophysics, a lot of geophysics, including seismic waves, the disturbances on the underground surface of the earth, these are being dealt with geophysics. So what we can summarize is that harmonic analysis actually provides tools for understanding complex phenomena through simpler periodic components. That means I divide those waves into simpler periodic components which keeps on repeating and repeating and repeating, and harmonic analysis with its sophisticated mathematics helps us to understand. We come to the next part, which is very important and something which I would love to explain with examples. It is what is actually a functional analysis. You see, functional analysis actually is basically dealing with functionals, or what we call functions of functions. Now, let me give you a quick example so that you can understand. So functional, when we talk what is a functional, it is a function. It is a relationship between objects, but the objects may be numbers, may be vectors or functions, and we group them together in something which is called a space. We will come to what is a space in mathematics, but first let us take a quick example. So we take a function and then we take a functional, and what this functional produces is basically a scalar, that is a number. And this number can be anything. It can be the average value of the function, it can be the maximum value it reaches, or it can be how smooth or wiggling up and down the function is doing. I will just explain with a clear example in the next part. So what we understand from here is a functional is a function, obviously, otherwise how would it happen, that takes the function as an input and returns a number as its output. Simple. It will take a number, and this number can be 1, 2, 3 or any value. Okay, let us quickly see an example. So I would like to request you to think this as a song. Okay, the song can be seen as a function where this one, that is the time, is the input, and the sound or volume is the output. Simple. Now a functional, if I relate this functional to the song, could be the average loudness of the song, this function. This one, this could be the average, it gives out a number which gives out that it is basically tells how loud the entire song is, or any value. So in a functional analysis, we study how these types of, I would say, rules work and how they can help us to analyze and understand different kinds of functions. So you can think this as a recipe also that takes ingredients, for example numbers, and cooks up a dish, another number. A function is like a special type of recipe that takes not just individual numbers but entire function as ingredients and produces a new number as the output. So it is like of having a magical cookbook, which you can say you can put into recipes into an ingredients, and instead of mixing flour and sugar, you might just tell the recipe that double all the ingredients, and the cookbook gives you a new recipe and the dish has been doubled. So that is how functional works. It takes a function and it gives the new function as a result, and functional analysis actually deals with these measurements kind of a thing. Okay, so for example, a quick example further. For example, if I take the integral of a function, then what would result is the functional, that is the area under the curve. So obviously the derivative of a function is definitely is a functional. If I take a derivative, the integral of a function is functional. If I take a derivative, then definitely it is again a functional, because it produces what is called the tangent of a line, or it produces the tangent of a line. So from here, what we deduce is this one. We get what is called this one. This functional analysis is basically a branch of mathematics that is interested in understanding these functionals that we just talked about and how they interact with function. So it is something like studying the rules that helps us to measure and compare the various functions. Now we come back, what are the aspects of functional analysis? First, obviously, you see the vectors. I don't have the time, otherwise I would have expanded each of the component. Maybe if I can do it in a separate video. So you see the vector spaces of functions. Function analysis again generalizes the concepts. Again, it is going towards generalization. Now this is something technical I won't explain right now. It will take a little bit of time. It's called normed and Banach spaces. So function analysis again introduces a concept of norms, and spaces occupied are called norm spaces. Again, understand it is a generalization. Again, inner product spaces and Hilbert spaces. So again, function analysis is extending the concept of inner product to function spaces, giving rise to inner product space. Linear operators, it studies linear operators that map functions. Compactness and convergence, very important. It deals with the concepts of compactness and various mode of convergence within function spaces. So just as I told you that these are being expanded on a space, so the functional is being studied by function, and we introduce a new concept which is called a mathematical space, and I will show you maybe in a later video how these extensions actually happens. We also find obviously the application in quantum mechanics because it deals with Hilbert spaces, and then we find something which is called a wavelet analysis, and then we find its applications in differential equations because it is used to solve partial and ODEs, so it provides a tool for understanding this. This covers the overall idea, what is a function analysis, what is function analysis, but the concept is, the question is that how function analysis at all has helped to change the entire scenario of mathematics, isn't it? Otherwise it would have no use. So let us look how function analysis has changed the scenario into this part of our video. So again, I would say it is a very, in a literary term, trying to explain, not using equations. So it is provided a very general and an abstract framework. What does that mean? That means it does not require functions, for example, to define a real number line, and it does not require them to be continuous or differentiable. It is more general and it works on more abstract spaces. Obviously, it has led to the development of new techniques. Function analysis has led to the development of very new techniques which actually has helped in different areas of mathematics. Also, what it has done is that it has unified. That means it has taken calculus, linear algebra, differential equation. It is just like a unification of physics. It is a unification of mathematics, where it has taken into different calculus, parts of linear algebra, differential equation, and it is unified. What does that mean? It becomes easy. What does that mean? It becomes all of them is in one plate, and you can do things much easier. So this actually shows that how function analysis have a new era which is dawning. It is already there, and it has provided a general abstract framework. It helps problem solving faster, and it unifies everything together. Now, in spite of function analysis, we remember that we deal with what? Numbers. Yes, and numbers would not have been possible with what is called a numerical analysis, coming up into the next part of our video. So what is numerical analysis? Well, numerical analysis is something which develops methods to solve mathematical problems approximately. Again, approximately, that is why I've underlined it in red. So there are solutions, often situations where exact solutions are not possible. So what we do is that we deal with the approximation of solution, and this is truly important in different areas of finance, engineering, biology, physics, chemistry, and whatnot, because we know in certain areas there are no exact solution. What are the aspects of numerical analysis? Let us have a quick look. So it develops approximations and algorithms. It can be used in computers and other systems, which just gives you the approximator. It determines the errors and accuracy that arises due to the approximation and to the limitations of finite precise mathematics. It also, remember, the numerical methods for finding of equations and roots. Obviously it helps it in interpolation and approximation, because polynomials are coming into play. Numerical differentiation and integration, so we can use the techniques for definite integrals and estimate. We just estimate. This is all about estimation. Derivatives are crucial in scientific analysis. So few other aspects: ordinary and partial derivative differential equation. Yes, so that this is equally important in order to know, because we always calculate with ODEs and PDEs, which takes a wide spectrum of physics, engineering, mathematics, chemistry, even biology. So numerical analysis actually helps into that. Question is that, again, has numerical analysis served anything beneficial for mankind, or it has made any significant contribution? Looking up, let us look into the next part of our video. Now again, this would be too technical to explain, but I'm just trying to give you a very basic layman's idea. There's something which is called finite element method, which is developed around 1950-55, and it is basically an revolutionize engineering, especially car industries, by approximating complex physical system, and it uses simple geometric elements. If you really want to know about finite element method, please do put up your comments. I would definitely do that. This is a great one. Fast Fourier transform, FFT. These actually does a lot of Fourier transform, which is specially used in signal processing and image analysis, much faster. So yeah, it does that. And there is something which is called quadrature rules, and this is also very technical, using Gauss's quadrature laws. And there is something called Runge-Kutta models, and these are widely used in solving ordinary differential equations, and especially for physics and engineering and things which are into dynamic system. I know this is a little bit hazy, terms are not clear, but anyway, this is how the numerical analysis contributes. Okay, so now it is a quick time that we have understood a lot of things. Let us summarize. So if we talk of the differences, it is no kind of a tabular structure where we can make the differences, but let us understand mathematical analysis is something very generic. It comprises a wide spectrum of mathematical analysis. We dealt with non-standard analysis, which is debated, but it has helped a lot. It has extended the traditional approach of calculus, including the infinitesimal numbers. We also know that harmonic analysis is something which is dealt with branch of mathematics into theoretical foundations, continuous signal, or something related to wave signal, and the underpinning structure is the Fourier transform or Fourier series. We saw functional analysis, which is much more abstract, but the concerned areas of functionals are dealt with, where spaces are combined. It is a unification of mathematics, Banach spaces, and other abstract things. And then we came to know what is a numerical analysis, which is basically producing algorithms and numbers which we used for approximation, and it is widely used because we always cannot come to know about the exact solutions. Now, what I have not covered is what is called a complex analysis, and I have made enough videos on the motivational part and the mathematics part. It is there in my playlist in complex analysis in physics for students. Go ahead and check it. And also there are 3 good and extended videos on reanalysis. What is that? What is reanalysis? How do we study? Prerequisites and everything. So these things are already being covered, and that completes our today's understanding of what is mathematical analysis. Again, a big note of thanks and for watching this video. Please do subscribe to my channel Physics for Students. Click on the bell icon to get all the notification from Physics for Students. As I'm always available in this email ID, you can subscribe to my other channel, and if you're really interested, please do follow me on Facebook and LinkedIn, Instagram and Twitter in order to know more about Physics for Students. Thank you very much for watching this video, and Physics for Students will be soon back with much more interesting, intriguing and exciting videos on physics and mathematics. Till then, goodbye.